So, you're worried about giving DeepSeek your data, but there's no need to worry because DeepSeek is open source, which means we can download it and run it locally on our own personal machines whenever and whatever we want, and without needing expensive GPUs at that. And no, having a model on your computer does not mean that you're giving your data to DeepSeek. It means that you have a bunch of floating point matrices that lets you output responses based on the inputs that you give them. So if you're like me and you find yourself on an airplane often without access to ChatGPT, or you want the absolute most secure way to interact with a cheap reasoning model, there is an alternative. And you can even take DeepSeek to the next level by allowing it to process documents locally on your machine with Retrieval-Augmented Generation. And I'm telling you about all of these things that you can do because we're going to be doing them today. We're going to download DeepSeek on a MacBook Pro using a tool called Ollama. Then we're going to build a simple web app that lets you query a PDF document using Retrieval-Augmented Generation with LangChain and Gradio. And if you're a Windows user, don't worry, I will be adding Windows-specific instructions along the video. My objective with this video is to give you as much details as possible around the Retrieval-Augmented Generation process while providing you a lot of intuition to make it accessible. So if you're a beginner or a practitioner, I'm hoping that you will get value nevertheless. If you have Python skills and a basic understanding of LLMs, you should be able to finish this video, so stick around for it. Just a note before we get started, today's video is a fork of Ashi Dutt's tutorial on the DataCamp blog of the same topic. Without her, this video would not be possible, so make sure to give her a follow and make sure to give her a shout out. And with that, let's get started. So I have slides here just to give you a bit of intuition on the Retrieval-Augmented Generation process and really give a bit of an explanation of what Retrieval-Augmented Generation tries to do. So you see here on the left-hand side, this picture of actually the high school that I went to. So I grew up in Beirut, Lebanon, and I went to the school called Lycée Abdelader, which is one of the oldest schools in Beirut. Here you see on the left-hand side a picture of one of the buildings almost 100 years ago versus a few years ago at the bottom. And it's a French school, and one of my favorite subjects throughout that entire curriculum was geography, because in the French curriculum, actually, geography had a really strong geopolitical component to it. So I love geopolitics. I love that topic. And one of the chapters in the final year of high schools that I really enjoyed was on American soft power. So our teacher would often give us exams where we would have to write a dissertation on the foundations of American soft power, where we'd need to talk about the power of Hollywood and how it's able to propagate ideas across the world, or the power of the American financial system. And these were really interesting topics to study at the time. However, one thing that really bugged me when I was writing the essays is that I did not have access to up-to-date data or the textbook or the ability to perform additional research. And this was actually hindered a lot of the quality of my writing, because there were moments that I wanted to go beyond what was written in the textbook, but I was not able to. And sometimes I was prone to mistakes and doing some factual errors. So we had an amazing teacher who would also allow us, especially when doing homework, to do, and she would encourage us to do internet search and Google search and read documents that go beyond the textbook. And in a lot of ways, this is the intuition behind Retrieval-Augmented Generation. Our teacher would allow us to generate an essay that was augmented by information that we would retrieve from the internet. And this is what Retrieval-Augmented Generation does. It allows LLMs to access documents or information that are stored in a database, specifically here a vector database, because we're looking at information that is stored as text, and reference that information to give a more accurate response. Now, we all know that LLMs are highly prone to hallucination, maybe less so with reasoning models, but nevertheless still prone to hallucination. And this reminds me of this paper that was written by Timnit Jibru, Emily Bender, Margaret Mitchell, and a few other folks on the dangers of stochastic parrots. So LLMs in a lot of ways are stochastic parrots. They just parrot back what is the most statistically likely thing that will satisfy the user prompt. And looking back at 2023, which feels like 5 years ago at this point, hallucinate was actually Cambridge's dictionary word of the year in 2023. And what Retrieval-Augmented Generation allows you to do is limit some of those hallucinations, ground the responses of your LLM with real world information. So for example, today we're going to be building a small web app that lets you process a PDF document. We're going to actually be uploading the DeepSeek V3 paper and asking a question about it. Had I asked the DeepSeek model that information without giving it that paper, it would have probably hallucinated a lot of the output. So ultimately, what we're going to be doing today, we're going to be taking DeepSeek and we're going to be augmenting it with the ability to read from documents and to pre-process PDF documents, which will hopefully ground its responses. And we're going to be able to host this on our local machine. And essentially, the tools that we're going to be using are Ollama, which allows us to download models locally. We're going to be using ChromaDB, which is an open source package that lets us set up simple vector databases. We're going to be using LangChain, which is one of the most popular frameworks for working with large language models and setting up retrieval-augmented generation pipelines. And then finally, to put it all together and host it in a web app, we're going to be using Gradio. So with that, let's get started by downloading Ollama, which we can have here on the website. All you need to do is go to ollama.com, press download. I'm going to be downloading for Mac OS. And as you can see here, it's going to be downloading. I'm going to open it. So I'm going to show folks here what it looks like for me. I'm going to press on Ollama. Yes, I do want to trust it. So let's move it to applications. And that's it. Ollama has been downloaded. I can check that it's downloaded by going to terminal, which I'll be doing shortly. And then one thing, I want to be able to download DeepSeek. So if you go and search for models on the Ollama website, and I type for DeepSeek, you'll find DeepSeek R1. Now, there are multiple versions of DeepSeek that you can download. There are 1.5 billion parameters, 7 billion parameters, 8 billion, 14, 60, 71 billion. So the trade-off here, the smaller the model, the easier it will run on your computer. The bigger the model, maybe the more accurate it will be, but it will be more computationally intensive. Now, for today's illustration, I'm going to be downloading the 1.5 billion parameter model. And all you need to do is just follow this piece of text here. So if I want to download the 1.5 billion parameter model, or I need to run on terminal, and I'll show you how it will look like shortly. Ollama run DeepSeek R1 1.5b. So I'm going to copy paste this, and then all you need to do is go on Spotlight if you're on MacBook Pro. I'll add the instructions on Windows on the screen here, and press on search for terminal, this really scary thing, and then open it. I already have it open. And then all you need to do is paste that code here, Ollama run DeepSeek R1 semicolon 1.5b, and it will download the DeepSeek 1.5 billion parameter model. So let's see how it goes. So yeah, it's pulling the manifest. It's downloading the model. Okay, and it's successful. And as you can see here now, I have a send a message, right? So I'm going to ask it, what is 25 times 25? So, and you can see here the chain of thought. It's thinking to calculate 25 multiplied by 25. I will use the standard multiplication method. And as you can see, it's pretty fast because we've downloaded the 1.5 billion parameter model. And then you can see here, it arrived at the final answer, 625. Let's just make sure that that is correct. Yeah, it is correct. Now, if you can see here on Ollama, there's this text that says for help, because I want to exit the chat. So I'm going to type this. And as you can see here, it can set session variables, show the model information, load a session or a model, save my current session. So here I can save my chat, for example, right? Or I can exit by saying bye-bye. So I can just type dash bye, and then I will exit the chat. Now, one additional command I will put here is Ollama serve. And what this allows is to have the Ollama DeepSeek server running in the background, the local server. So I'm just going to keep it here. So yeah, it's already running. And here what I can do, for example, is use a curl command to query DeepSeek using an API command, right? So what I'm doing here is I'm just typing here curl. And as you can see, the local host is 11434. So I'll just do localhost 11434, and I'll use here the API chat. Here I just want to clarify, we are querying it locally, right? But we're just locally querying it from the local host that it's running on. So here I'm gonna type in the message. So the model is DeepSeek R1 1.5b. The messages are, so I'm gonna give it the role. Oops, this is a dictionary. So it is here the user, and the content is solve 25 times 25. Let me just remove this bottle of water. And then close it here. And then stream, I'm going to set it to false. And then let's see what happens. So I'm running the model locally here. I'm running it. And as you can see, it queried it, and then it took the role of the assistant. So I need to solve multiplication of 25 by 25. First, I will write down the number vertically, aligned for clarity, so on and so forth. Yeah, and it arrived at 62. Did it arrive at the result? Yes, 625, as you can see here. So it's working. We have DeepSeek running on our local machine. And now we can get started with our notebook. So all I need to do, I'm going to run this locally again. It's all local code. So I'm going to just jump into Jupyter Notebook. This is my IDE of choice, but you can do this in any IDE that you have on your machine. And you'll see here, I'm going to get an open Jupyter Notebook. Let me just, let me zoom in here a bit. And I already have a couple of notebook open. So as you can see, I have a DeepSeek Gradio RAG file. I have a walkthrough file and a solution code. The solution code will be posted in the description link below, so check it out. We will link it in a DataCamp workspace. All you need to do is just download the notebook and run it. And then we will run it from there. So we have our notebook open now, and essentially what we're going to be doing is building a simple web app that lets us upload a document, a PDF document to Gradio, which is, I'll explain what Gradio is shortly, and lets us query DeepSeek R1 using that document. So to be able to build this chatbot, all we need to do is first install and import a few packages. So we're going to be installing Ollama, and this package, what it allows us to do essentially is run LLMs locally. So this is just the package version of Ollama. And then we're going to be using LangChain, which is a pretty popular framework for LLMs to build retrieval-augmented generation pipelines, process data, integrate LLMs together, so on and so forth. Then we're going to be using ChromaDB, which is a vector database that lets us retrieve and store text embeddings. Now, don't worry about embeddings. I will make sure to explain what embeddings are. And then we're going to be using Gradio, which is a simple framework that lets us build web-based interfaces for machine learning models. Then LangChain Community, which is a collection of integrations and utilities that extend LangChain that make it easier even to work with a few of the packages that we'll be using today. And then finally, PyMu PDF, which allows us to work with PDF documents when processing them. So I've already installed these particular packages, so all you need to do is run this cell here below. Now you can hit here pip install Ollama. You can see I already have a lot of the requirements already satisfied. And then what we need to do is just import our packages. So we're going to be importing Ollama, and what this allows is better interaction with the LLMs. And then importing Gradio as GR. So this helps us create the easy to use web interface. Then for document processing and retrieval, we're going to be using from LangChain community.document loaders, import PyMu PDF loader. What this allows us to do is just process PDF documents. Then from LangChain.TextSplitter, import recursive character text splitter. This splits text into smaller chunks because LLMs understand text data in smaller chunks more easily. Then from LangChain.VectorStores, we're going to import Chroma. And what this allows is just the storage of the text embedding. Again, don't worry about embeddings. We're going to cover them shortly. And then for embedding generation, again, I repeat, don't worry about them. We're going to cover them shortly. We're going to get from LangChain community.embeddings, import Ollama embeddings. And then we're going to import regular expressions as well, just to make our life easier for us. So I've imported it here. And then now, we're good to get started. We're going to actually test out querying DeepSeek R1 using this Python cell here. So here in this snippet, we're going to be using Ollama.chat, right? And we're going to be passing a few parameters, a few arguments, right? So what I'll do is I'm going to define this response variable, right? So Ollama.chat. And I'm going to be, first, let me close the function. So I'm going to be using my model, which is DeepSeek R1 1.5b. And that is it, right? So here I'm specifying that the model that I'm using is DeepSeek R1. Note that you can have multiple models downloaded locally and you can choose which one you want. So you can have, for example, Mistral or Llama, right? Second thing, I'm going to be specifying my messages, similar to that curl function that we just defined. So here it is. So my role is the user, and then content is going to be explain Newton's second law of motion. Right, and then here I'm going to close the bracket, right? And then what I'm going to do is I'm going to print the first response that you can see here. So response message. And I'm going to print the content of the message. And then let's see, it's going to take about maybe a minute or so, because we're creating it locally. Okay, so we have these thinking tags. All right, so I need to explain Newton's second law of motion. I don't know about the physics class. I know about this from my physics class. That's pretty funny. I remember that Newton's laws are the foundation of classical mechanics. There are 3 ones, so on and so forth. And then, yeah, as you can see with DeepSeek, the chain of thought is really long. And then it provided here the second law of motion explained, key concepts, examples and applications, real-world implications, and conclusion. So we are able to run our LLM. So now we're good to move to pre-processing the PDF document for retrieval-augmented generation. So what we're going to create now is a function that pre-processes the PDF file for rank. And here's the logic that we're going to be breaking it down in. So as you can see, I'm really going to try to focus on going step by step here. First, we're going to see if the PDF is provided. If it's not provided, it returns none so that the vector database does not get any errors. Then we're going to extract the text from the PDF using the PyMu PDF loader function, right? We're going to split that text into chunks, right? And I'll show you how we're going to be doing it. For each of those chunks, I'm going to be generating embeddings, right? And what these embeddings allow us to do, and I'll go through them in a bit more, they'll be able to help us find semantic meaning-based matches rather than exact keyword matches, right? And I'll explain what I mean by semantic meaning. Then we're going to store the embeddings in a vector database, right? And then create a retriever to search the data set. So the retriever essentially acts like a search engine, right? And then the function will return like 3 components: a text splitter object that allows for future text processing, the vector store, so where the documents are embedded, right? And then retriever, which allows for search over the document. So I'll walk you through the logic one by one, and it will be clearer as we write the function. So what are embeddings? Embeddings are essentially numerical representations of text that capture the meaning of the word that we have, right? So instead of like treating words as like a letter of like a sequence of letters, embeddings transform them into multi-dimensional vectors in a graph that you can see here, right? Where similar sentences and words are grouped together. So, for example, the distance between man and woman and king to queen on this vector plane is on this multi-dimensional plane is similar because they have a similar semantic relationship. Similar the relationship between walked and walking and swimming and swam, right? Even though they're completely different letters, they're completely unrelated, but the vector meaning, the meaning of them is represented in similar distance on the multidimensional plane, right? So essentially what we're trying to do here is go beyond just like the text content itself, but also capture the meaning of the word and represent the meaning of the word where it fits in a sentence, right? So, words with similar meanings at the end of the day are closer together, and words with different meanings are further apart. So a good example would be cat and dog will be closer together on the embedding space than cat and car, even though cat and car shares more characters than cat and dog. And this is essentially how it's calculated. And it's calculated based on the similar context in sentences, so it's trained on a lot of text data, and data that's in similar context will be grouped together, right? So when a user asks an LLM a question, it doesn't look for just exact matches on the characters, it also looks for meaning. So what this means and why this matters for our process is that by storing our PDFs as an embedding, when an LLM queries, it's not only able to look at exact matches, but it's also able to look at meaning and semantic definitions of the content rather than just like doing matches on the exact characters. So with that said, let's create the function that lets us process the PDF. It's going to be called process PDF, surprise, surprise. So what I'm going to do first, I'm going to create this function that says define a process PDF, and it's going to take this input as PDF bytes, which is a PDF file. Now, first thing I'm going to do is that if the PDF file is empty, it returns none, and this prevents errors from the LLM trying to prevent empty input. So if PDF bytes is none, then return none, none. So here is, let me fix this here. None, none, none. And I'm adding these three outputs because this is how the vector database will be set up. Now, second thing I'm going to be doing, I'm going to be creating this loader object using the PyMu PDF loader function. That's essentially what it does is that it initializes the PDF file. It creates the PDF file. And then what I'm going to do is I'm going to create this data object where I use the loader.load. So I use the .load method from the loader object. And what this does, just extracts the text of the PDF file that I'm creating. And next thing I'm going to do is I'm going to split my text so that they're defined into chunks. So I'm going to split the PDF file that I give it into small chunks so that it's easy for the LLM to process. LLMs, they like to read the text in small chunks, and this is what I'm going to do. So what I'm going to be doing here, I'm going to be creating this text splitter object, and then I'm going to be using the recursive character text splitter function that I imported earlier from LangChain. I'm going to define my chunk size equals 500. So each, the PDF file will be split into different chunks of 500 characters each. And in order for the context to remain between chunk 1 and chunk 2, what I'm going to do is I'm going to create a chunk overlap of equals 100. So between each chunk, there's going to be an overlap of 100 characters. So just to visualize this, let's assume that this notebook here that we have is actually a PDF file that we're giving into, we're inputting into this function. The first chunk will be maybe this section here. And then let's assume that these are 500 characters. And the second chunk will essentially be here. So these 100 characters plus an additional 400 characters from the new chunk below. And then, so I've defined my text splitter function. And then I'm going to create a chunks object, right? Which is essentially, splitting the data into different chunks. So I'm going to split documents here of the data, right? And then what I'm going to do, I'm going to create my embeddings. So I'm going to create my embeddings from my embedding model, and I'm going to be using DeepSeek R1 to create my embedding model. So I'm going to create embeddings here equals Ollama embeddings. And the model that I'm going to be using is that, guess what? DeepSeek R1 1.5b. And then therefore I'm going to go to words. So far, let's do a bit of a recap. We set up the logic so that if the PDF file is empty, it returns none. We load the PDF file. We extract the data from the PDF file. We define a text splitter object that splits the PDF file into multiple chunks of 500 characters each with a 100 character chunk overlap. We split the documents into chunks. Now we define the embedding model, right? And then what I'm going to do, I'm going to define the vector database using vector store. I'm going to call it a vector store, and I'm going to do chroma from documents. So this takes in the PDF file, creates a vector database from the PDF file, where the documents is equal chunks. So these are my documents, right? The embeddings is my embeddings model that I created. And I'm going to add here persist directory equals chroma db. And what this does is just lets me create a directory where this data is stored, right? Now, last thing I'm going to do is create a retriever object. So retriever, what it does is that it enables searching through the vector store. It's an object that lets me retrieve from the vector store the information that I need. So vector store as retriever, so that we can see here. And then I'm going to return 3 objects. I'm going to return the text splitter because I'm going to need this further down the line. I'm going to return the vector store, and I'm going to return the retriever. And what we're doing here is that the text splitter will be used to split any new text in the same way as before. The vector store will be able to hold the processed document chunks, and the retriever will be used to fetch any relevant chunks when answering questions. So I'm going to run this here, and it should be good to go. Now, the second thing that I'm going to do is I want to combine the retrieved document chunks, right? So once the embeddings are retrieved, next we need to stitch these together, right? So what the combine docs function does, it merges multiple retrieved document chunks into a single string. So why do we do this? It provides better context. That way, the LLM has structured continuous text better than fragmented pieces. It improves the quality of the response. It preserves the document flow and the context, and it also optimizes token usage. So what I'm going to do now is I'm going to define this pretty simple function called define combine docs, which takes into as input the chunks. And then what it returns is I'm going to be using regular expressions here. I'm going to break line twice between the different documents, where doc page content for doc and docs. So for each doc and the docs input that I get here, we return them in a single text, where each doc is broken down by 2 different 2 line breaks, right? So this essentially is the step that we've almost finalized on pre-processing the PDF file. Now that we have pre-processed the PDF, that we've defined the function that pre-processes the PDF, what we want to do is format the inputs in a way that are legible by DeepSeek R1, right? And provides an output. So what we want to do is combine the input with the document that we're going to upload and create a function that creates the logic for that. So how this function will work, it formats the input, so it structures the question plus the context from the PDF document and for better input understanding. It calls DeepSeek R1, so it sends the formatted prompt to generate a response. It extracts the response content, right? And then it cleans any unnecessary text using the think tags, so on and so forth, so that we can just have a clean response, right? And returns the cleaned response. So what I'm going to do, I'm going to create this Ollama LLM function, right? Which takes in as input question and the context, right? And what it does, I'm going to first create this formatted prompt object. And what are we going to do here is we're going to format the prompt with the question and the context to provide like a structured input for the LLM. So I'm going to be using here this set of code. So question is the question input that you can see. All right. And then I'm going to break line here a couple of times. And then context is my context object, right? So the formatted prompt essentially, here's the question, break line, here's the context, right? And then we're going to generate a response. And we already did this before. So we're going to be using Ollama chat. The model is DeepSeek R1 1.5b. And then our messages will be, so our role is user. And then the content, what is it? Is the formatted prompt. Okay, and then we're gonna close the parentheses, and then we're gonna extract the response. So response content equals response, I think message, sorry, and then content. Oops. And then finally, we want to clean up a bit of the final answer. So we're going to be using here regular expressions. So what we're doing here, I'm doing this re.sub function. So this is substitute, right? And what I'm going to do is I'm going to replace, we're just going to be searching for any of these thinking tags, right? So here, I used, I'm using code here for the regular expressions that was already provided from the tutorial and I got from ChatGPT. I'm not really good at regular expressions. And then here, what we're searching for are think tags, right? So we're searching anything that contains think tags. And then what we're doing, not sure why indentation is not working here. We're going to replace them with empty spaces. Sorry for missing that. Yeah, we're going to replace them with empty spaces in the response content. And then we're going to do flags equal re.all. And we're going to strip the response. So what this re.all does is that we treat dots as new lines. That's essentially just an update to the regular expression logic that we're creating, right? And then we're going to return the final answer. So I'll just go through this again. What we did is that we have the context from the chunks that we've created in the PDF document that we created. We have the question that we want to ask R1. So what we're going to do is format the prompt as here's the question, here's the context. The response from Ollama will be generated based on the formatted prompt. And then what we do is use some regular expressions to remove anything before the think tags and just get the response content, right? And then we return the final question, the final answer. Now, we have a couple of steps left. And essentially what we're going to do now is build the RAG pipeline. Right, so we've defined a few of these functions before, right? And now we're gonna put them together, right? So how does the RAG pipeline work? We're gonna create a define LangChain function, so a LangChain function that takes as input the question we're gonna ask the LLM. It's gonna take the text splitter object we created earlier, the vector store to retrieve information from, and the retriever object to retrieve that information from the vector store. So what we'll be doing is first, the function will retrieve any information related to the question using semantic search, using the embeddings that we've done, right? And then what it will do is that it will format the content, the retrieved documents. It will combine them, similar with using this function that we did. So for any relevant information that has been found related to this question, we're going to combine it into one single query, right? And then we're going to ask Ollama a question with the question plus the formatted content as context. So what I'm going to do is I'm going to set this retrieve documents equal retriever dot invoke question, right? So what we're doing here is that for the question, we're going to be looking at the vector store, and we're going to be looking at any relevant information in the vector store related to the question. Then we're going to do formatted content equals combine docs retrieved docs. So for any of these documents that were retrieved, we're going to combine them into one big text. And then all we're going to do is return Ollama LLM. So we're going to, the query, the response from DeepSeek R1. And this is the question. And this is the formatted content. So this is the RAG chain, essentially. It's a really simplified retrieval-augmented generation chain, right? And now we're going to put it all together. So we're going to create an ask questions function, because this is essentially the logic of the interface we're trying to build, right? So I'm going to define ask question. It takes as input a PDF file and a question, right? So we have the PDF file, and then we have the input that we want to ask the LLM to, right? We define the text splitter, vector store, and retriever objects from processing the PDF, right? And then if the text splitter is none, return none. So if you remember, right, we had these process PDF. If the PDF bytes is empty, it's none, right? So if the PDF bytes is none, the text splitter is none, so we're returning nothing. And then if the text splitter is not none, the results will be the RAG chain that we defined here. So I go here, question, text splitter, vector store, retriever. And I'm going to return my result. So I'll explain the logic here again from the top. So first thing that we've done is here we tested out DeepSeek. Now, first thing that we did is created a process PDF function. And what this does is that takes the PDF and creates the text splitter function, creates the embeddings from the PDF, stores that information in the vector store, and then we define the retriever object that lets us retrieve the information from the vector store. So this function determines the logic of processing the PDF. Then what this function does is that whenever we have chunks, we combine them into a long text, right? Then what this function does is that we provide DeepSeek R1 a query with additional context, right? Based on with that context being formatted, right, into one long text. And what this function does is just put it all together. We have the logic of the processing the PDF. We get that context from the PDF, and we search for the context based on the question using the embeddings model that we created, right? And the retriever logic here. We get the information from the retriever function, and then we format them into one long text, and then we return a response from DeepSeek with that combined context. So with that said, now all we need to do is run the interface with Gradio. So what we're going to create here is an interface using the Gradio import that we imported as gr interface. Okay, so the function here, this is the function that processes the input and generates the output. So this is essentially the logic of the app, right? So fn equals ask question. So here, what we do, we get the PDF. The result is the LangChain, right? And the inputs. So what are the inputs that we're gonna take into the application itself? So this is all Gradio syntax. It's okay if you're not necessarily attuned or aware of the syntax. It's essentially just we're building a web app here, right? We're gonna get a file object, right, with the label that says upload PDF, and we're gonna set it to optional, right? So what this essentially allows us to do is to upload a PDF file, right? And then I'm gonna do a text box that says label equals ask a question. So this is where my query goes in, right? And these are essentially my inputs. And now, I forgot here. And then my outputs are going to be the text. And then the title will be ask questions about your PDF. I'm just going to add a bit of a description. Use DeepSeek R1 1.5b to answer questions about your uploaded PDF document. And that's essentially the interface. And then what I'm going to do, interface.launch. Ooh, I have an error here. On line 6. Oh, we forgot a parentheses. Okay, boom. We have a interface. Let's see, we still don't know if it's going to work or not because I may have done an error above in my logic applications. But what I'm going to do is I'm going to upload the DeepSeek V3 paper that was released almost in December. It feels like a millennium ago. And what I'm going to ask here is what are the accuracy, what are the different benchmarks used in this paper? Ooh, I got an error. So I made a mistake at one point. Yes. So let's see if it runs again. Okay, it's processing. Let's see what happens. Okay, so now we have a working chat interface with Gradio. So what we're gonna do here is we've uploaded the DeepSeek V3 PDF paper, right? We asked it questions. What are the different benchmarks in this paper? And it gave us an output that's not as good as I hoped it was, but it does actually stick to some of the core aspects of the paper. So the paper discusses DeepSeek V3, the focus on its architecture, introduced features like multi-head latent attention for efficiency and DeepSeek mixture of experts for economy, the core contributions, the multi-token prediction training object, so on and so forth. And with that, you've been able to build a simple RAG bot that creates based on the DeepSeek R1 model more input with improves the input of the DeepSeek R1 model with more documents and context based on the documents that you provide. And this is essentially a simple chatbot environment that we can run on our local URL with this link. And it's running locally. You don't need the internet. It's private. It's running all on your machine. Now, this wraps up the walkthrough for today, but I do want to mention one last thing is that if you want to uninstall Ollama in DeepSeek, all what you need to do is follow the steps here below. So to uninstall Ollama, you just need to delete Ollama from your applications on macOS. On Windows, you need to uninstall Ollama using Control Panel. To uninstall DeepSeek, you need to search for these folders on your computer and delete these folders. So on macOS, you'll go to Ollama Models, delete all the folders there, and then Windows, you need to input your username here, but find the Ollama Models here as well and delete everything. And that's it for today's video on building a simple RAG bot using DeepSeek that runs locally on your machine. Now, what we did today was completely safe and secure because all we did was download a bunch of floating point matrices that generate an output based on the input that you give them. Now, that said, I'll leave you to additional learning materials that you can check out in the description below. And with that, happy learning.